Hi everyone. In this video we will be discussing radii and intervals of convergence for power series. I pulled a handful of problems from the 9th edition of Stewart's textbook, section 11.8. And we'll see how these work. So let's dive right in. Number 15. Basically anytime you're asked to find an interval of convergence, ratio test is the way to go. Right? You know that a series converges whenever the limit that you calculate in the ratio test turns out to be less than 1. So we can set this up the way we normally would. Look at the limit of the absolute value of the ratio of, I'm going to write the an plus first term here, and then the a sub nth term here. So replacing all my n's by n plus 1's, this would look like x to the n plus 1 over n plus 1 to the fourth times 4 to the n plus 1. And then on the bottom, I'll just reproduce what the terms in the series looked like to start with. Of course, it's annoying to write that out as one big fraction, so usually it's nicer to just multiply by the reciprocal, and sometimes I'll skip ahead and just do this from the get-go, but I figured I'd do it the long way to start with. Okay, keep the big numerator the same, and then multiply by the reciprocal of the big denominator. Okay. And then the great thing about ratio test is that usually there's a lot of simplification that happens. So limit, it looks like all but one of the x's will cancel. So let's leave that alone for now. All but one of the 4's will cancel. So there will be a 4 left in the denominator. So let's just have some fraction here, and I'll put a 4 down here. I said there'd be an x left over. I'm going to put that out back. You'll see why in a second. So that handles the x's. That handles the powers of 4. I also need to handle the powers of n, or n plus 1. Let's just write that out. N to the fourth and n plus 1 to the fourth hang around. And that looks good to me. The next thing I could do is I could do a couple things. First of all, this absolute value is annoying, but you can sort of see that, okay, 4 is positive, n is always positive because n goes from 1 to infinity. N plus 1 is always positive, powers of n are always positive. So the stuff that I wrote in that fraction doesn't actually need to be within absolute value bars. And the terms involving n, they're both to the 4th power, so let's just write n over n plus 1 to the 4th power. The thing I haven't talked about is the x. What happens when I take the absolute value of that? Well, as far as we know, x could be any number. So x might be negative. There's no reason why x has to always be positive. So let's keep the absolute value bars around that. All right, then we take the limit, and you can do this a number of ways. Whether you want to, I'll write some options in purple. Let's just focus on this fraction to the 4th power here. If you wanted to, you could write that as, you could do something kind of magical like this, and then split it up into that fraction minus that fraction. So the n plus 1 over n plus 1 is just 1, minus 1 over n plus 1 to the 4th. And then you can basically hand wave and say that goes to 0, so this goes to 1. That's sort of a funny way of doing it. If you don't like that, you could just push the limit inside, and then you're really just asking what's the limit as n goes to infinity of n over n plus 1. And you could do the same trick, or you could do L'Hopital's rule. Take a derivative of top and bottom, you get 1 over 1, which is 1. And there are other ways you could FOIL it all out if you wanted to. But in any case, this term approaches 1. So don't forget about this 1/4 out front. That means the limit is 1/4 times the absolute value of x. Right? Note that n and x basically have no relation to each other. We're taking the limit as n goes to infinity, so we can just sort of leave x alone. And then the question becomes, right, the ratio test asks, when is that limit less than 1? If it's less than 1 for some value of x, then that means that value of x causes this series to converge. I mean, power series are weird because you can plug in any number of values for x, and for some you might get convergence, for others you might get divergence. But this is something we can solve just algebraically, right? I could say, well, this is equivalent to writing multiply both sides by 4. That's equivalent to writing absolute value of x is less than 4. And if you remember how inequalities involving absolute values work, well, how can the absolute value of a number be less than 4? Well, if x is negative, well, if x is positive, then x better be less than 4. If x is positive, it could be, between 0 and -4. I hope I said if x is negative there. I may have misspoke. But anyway, basically this means x is between -4 and +4. Right? Any numbers within there have absolute value less than 4. And so you might say we're done. That's our interval of convergence. Ta-da. In fact, you can say one thing. You can say that this 4 is your radius of convergence. But you can't be sure that this is the interval of convergence. It's some subset of the interval of convergence. Certainly every x value between -4 and 4 will give me convergence. That's what we just showed using the ratio test. But there could be others. Right? There could be others because there's this other side case to the ratio test, which people often forget about, which is, okay, what if the limit I calculated isn't less than 1, but it's equal to 1? And if it's equal to 1, the ratio test has no conclusion, which means maybe it converges, maybe it diverges. If this is bigger than 1, it definitely diverges, so I don't even need to think about that to find the interval of convergence. But I do need to address what happens when the absolute value here is equal to 1. So basically the math is the same. Instead of an inequality, I have an equal sign, so maybe you're not too surprised to see, well, let's write it out, I suppose. 1/4 absolute value of x equals 1. If I multiply both sides by 4, that's the same as absolute value of x equals 4, and that's equivalent to x being either +4 or -4. Video is blocking that, apologies. Basically, no matter, basically you're just looking at the endpoints of this interval that you found in the previous step. Those are the extent where the ratio test might just give no conclusion. But if we actually check these, then we can see what happens. So let me scoot the next problem down. So I'll say at x equals -4 and at x equals +4. And then we'll end up with some interval of convergence at the end. Okay, just to prep us, the interval of convergence is going to be -4 to 4. I just don't know if it's going to be open parentheses, closed brackets, or some combination of those. We'll see. So I'll leave that without any parentheses for now. And if I'm looking at the case where x equals -4, then what do I get? Well, I should take this and actually plug it in for x here. So the series would look like the sum from n equals 1 to infinity, -4 to the n, over n to the 4, 4 to the n. And hopefully you see something nice here. More often than not, when you're checking endpoints like this, nice things do happen. In particular, -4 to the n over 4 to the n. Those are both to the power of n. -4 over 4 is -1. So this is really just, whoops. This is really just, move that, I guess. -1 to the n over n to the 4th power. And that is something that hopefully by this point we can just say converges. You can apply any number of tests to determine that. I would just say, by the alternating series test probably. And of course, when you're writing your solution down, you should be more thorough than me, and you should actually list out the requirements to pass the alternating series test. You have to show this thing is decreasing, and you have to show it's the limit is 0. I suppose there's a quicker way. You could just say it's absolutely convergent, because if I took the absolute value of those terms, I would get 1 over n to the 4th, and that's a p-series with p greater than 1. So it's absolutely convergent, and any absolutely convergent series is convergent. Feel free to do it that way too, that's faster. But in any case, you get convergence, which says to me that, okay, this particular value of x is in my interval of convergence, right? This -4 should be included in the interval. So I would have been wrong to put a parenthesis here. I really need a square bracket. Nothing less than -4 will give me convergence, but -4 itself does. How about +4? So again, I look back at the original series, I plug 4 in for x, and you'll see a nice little pattern here. I get almost the same thing, but it's not going to be alternating anymore. So my x to the n becomes 4 to the n to the 4th times 4 to the n. Now you see the 4 to the n's just cancel. So I'm just looking at 1 over n to the 4th. Okay, again, that's a p-series, so that converges. So I have to include this endpoint as well. So both 4 and -4 give me convergence in the original power series. So that's my interval of convergence. The radius of convergence is still 4. Right, the radius won't change if you add a single point. A single point sort of has size 0. So, but the endpoints are being included, and that's important to note. Okay, problem 25. Let's go through this one a little bit quicker. So let's set up our ratio test, and let's just do the n plus first term, and then let's multiply by the reciprocal of the nth term. Just saving myself a little writing. Then we can note that, again, most of these terms are positive. The n's and n plus 1's at least. The x minus 2's, who knows? The absolute value might affect those. So let's note that I have an x minus 2 to the n plus 1 and an x minus 2 to the n, so most of those cancel. I'll be left with 1 x minus 2, which I will need to keep in absolute value bars, because again, it might be positive or negative. And then the other pieces I'll just leave alone for now, n to the n over n plus 1 to the n plus 1. That looks like a hard limit to calculate. Right, n to the n over n plus 1 to the n plus 1. Looks hideous. If you think about it for a while, you might come to the conclusion that it's nice to maybe get both of these to be to the nth power. How can you do that? Well, a little bit of algebraic manipulation saves the day. I could peel off a factor of n plus 1 on the bottom. That leaves me with n plus 1 to the n. Still n plus 1 copies of n plus 1, but I peeled one of them off. On top, let's just leave it as is, n to the n. And then x minus 2 in absolute value. And now if I just focus on these two pieces, raise both of those to the nth power. Limit as n goes to infinity. So I still have this 1 over n plus 1 kind of hanging out on the outside. And then I have n over n plus 1 to the nth power, x minus 2 in absolute value. Okay. You might look at this and say this is still a hard limit to calculate. But if I rewrite it, you may recognize it. It's sort of a subtle thing, but you may have encountered this in Calc 1. This could be written, again, I could do my trick of like plus 1 minus 1, and then split it up into two pieces. So this is actually 1 minus 1 over n plus 1 to the n. Still looks ugly. Definitely still looks ugly. But it can be shown that this term, let's write this in purple off here, so here's the fact you might remember. This is a famous limit that goes to e. Our limit looks different than that, but the negative sign basically just makes this go to 1 over e. The negative sign becomes a negative power, so it's e to the negative 1, but that becomes 1 over e. You can spend some time proving this using some limit tricks, like take the natural logarithm and then try to get a L'Hopital's rule type thing out of it. But in any case, that goes to 1 over e. This limit, that'll just go to 0, right? So both of those limits exist. One of them goes to 0, one of them goes to some finite number, so their product should go to 0. So this guy went to 0, so this whole limit is 0, which is an unusual thing to get in the ratio test, but it does happen sometimes. So the question becomes, it's a silly question to write, but the ratio test always wants to know when the limit you calculated is less than 1. The answer is always. 0 is always less than 1. Essentially what I'm saying here is it doesn't matter what x is. Right? The fact that we had an n plus 1 on the bottom of that fraction when we were taking the limit means x could be huge, the limit's still going to go to 0, and so the interval of convergence here, well, any value of x works. So you would say negative infinity to positive infinity. And you would say the radius is infinite, the radius of convergence. Cool. Let's continue to number 31. Again, actually, before I continue, I sort of just noticed you could probably do root test on this. Let's do this in purple. If I wanted to do root test, I could have done limit as n goes to infinity, take the nth root of the absolute value of these terms. The absolute value won't matter too much. Absolute values play nice with exponents, so hopefully you trust me that this would just end up looking like absolute value x minus 2 over n. Right, basically, the nth root cancels both of these nth powers. And I don't need absolute value bars on n because it's already positive, so and then that's 0. Ta-da! 0 is always less than 1. Same answer. So you don't see root test being used a lot in interval of convergence problems, but I mean, if everything's raised to the power of n, might as well. It actually works out the same. So, great. Now let's continue to number 31. Again, I just want to do ratio test. N factorial, that's good to see for ratio test. Same for the power of n on the other term. So if I set this up, my n plus first term divided by my nth term. I forgot a factorial up top. Give me 1 second to put that in. Okay, nth term. Okay, as always, whenever you have some x involved, you get a ton of cancellation. We're just going to be left with some 2x minus 1. Again, I'm going to put it on the end. The next question is what happens to the factorials? Well, we know that, let me write this in the right color, do a little note, n plus 1 factorial over n factorial. Well, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 times n minus 3. Keep subtracting 1 until you get down to 2 and 1. And the thing you could notice here is that this part of it is just n factorial. So let's just rewrite this. I have an n factorial here. There's also an n factorial on the bottom, of course. Haven't done anything with that yet. And n factorial over itself is 1, so I just get n plus 1 out of this. So let's put that here. What is this limit? Again, don't worry too much about the x. We're only thinking about n changing. Well, the limit as n goes to infinity of n plus 1 is infinity. So, question. When is infinity less than 1? Answer, never, of course. But there's a slight hiccup. Very slight hiccup. This one's easy to miss. What actually happened? What actually happens if, like, I was dividing by 0 when I did this? Right? Maybe setting up the ratio test like this isn't even valid. Maybe 2x minus 1 is equal to 0, and then I can't actually write that fraction. It doesn't make sense. So, what if 2x minus 1 equals, I could write to the nth power, but that's the same as just asking if 2x minus 1 itself is equal to 0. Well, that would be, 2x equals 1, and so x equals a half. And if you actually plug in a half and, see what happens, to the series, it would look like still the sum from n equals 2 to infinity, n factorial, 2 times a half minus 1 to the n. But as you guys can see, 2 times a half minus 1 is 0. Right, so this term is 0 to the n. I'm just adding a bunch of zeros, I get 0. And, well, 0 is less than 1. So, I would say this particular choice of x gives you a convergent series. It's convergent in, a dumb way. It's just 0 added with itself infinitely many times is 0, but it's still a valid point within the quote-unquote interval of convergence. This answer, though, says no other points work. You could try plugging in a point just barely to the left of a half or just barely to the right of a half, and the series would diverge. You could try that if you want. Try plugging in some nearby values and see that the series explodes. Well, either explodes or alternates back and forth forever. I think it will explode, though. Well, yeah, it should explode. Okay. So my interval of convergence is actually not an interval at all. Oftentimes, if it's just one point, you write it within curly braces. And the radius of convergence is 0, because the size of a single point is 0. All right. Next problem. Again, ratio test should do the trick for us, so let's see how it works. Let's replace n with n plus 1 in both of these terms. Multiply by the reciprocal of what we started with. And what kind of cancellation do we get? Well, I can't actually cancel much from the ends, but I could say, it's a single fraction to the third power. On the other hand, for the x's, same sort of thing happens. I get just a single 5x minus 4 left over, and that's the only piece I need to include in absolute value bars. It's the only piece that could be negative. Again, by whatever logic you want to use, this piece goes to 1 when I let n go to infinity. So I just get absolute value of 5x minus 4 when I take that limit. And I'm checking when 5x minus 4 is less than 1. That happens, let's see, 5x minus 4. Again, anytime you have an inequality involving absolute values, you just say, well, that means the quantity that I'm taking the absolute value of has to be between whatever number's on the right and it's negative. And that's equivalent. Let's add 4 everywhere. So I get 3 on the left, 5x in the middle, 5 on the right. Let's divide everything by 5, and I get x is between 3/5 and 1. Okay, so the interval of convergence is at least that. Again, I have to check the endpoints. The radius of convergence is just going to be 1/5, because, just 1/5, because the center of this interval of convergence is whatever's halfway between these, which is 4/5. So, 1/5 on either side of it. But yes, let's check our endpoints. It's not guaranteed that both of them will be in here. Maybe neither will. Let's see. So at x equals 3 over 5, we're looking at the series n equals 1 to infinity. 5 times 3/5 minus 4 to the nth power. You should pretty much always get nice cancellation when you plug in endpoints here. In our case, 5 times 3/5 is 3, minus 4 is negative 1. So I get an alternating series, similar to that, I think, the first problem. We know this is convergent because it's absolutely convergent, because 1 over n cubed is a p-series that converges. Or you can do the alternating series test. How about our other endpoint at 1? Plugging x equals 1 in would give us 5 times 1 minus 4 all over n cubed, and of course that's 5 minus 4 is 1, 1 to the n is just 1. That converges as well. again by p-series. So my interval of convergence, I knew any point between 3/5 and 1 was in there, but actually the endpoints themselves are as well. Again, that's not guaranteed to happen. Both of those may have ended up being parentheses, in the case that these didn't converge. Maybe only one of them would, but in this case, both. Last problem I'm going to do is a slightly weird one. So suppose we have a power series. By the way, this C sub n is just saying, imagine these are arbitrary constants. C stands for constant. Sub n means maybe the constant changes for each n value. So I don't have to know what the CNs are. They're just numbers. We can mostly ignore those. And I'm told that this power series converges for a certain value of x and diverges for another value of x. Then I get asked about 4 other series which maybe look related to the series I'm thinking of. The first thing I'm going to advise you to do here is write this in a way that you can more easily see what the center of the interval of convergence will be. So since it's just x to the n, it's not like x minus 2 to the n or something. Let's write it as x minus 0 to the n, and note that the interval of convergence, when I write it like this, has center x equals 0. So when I'm imagining what my interval of convergence will be, it'll be some interval centered on the origin, centered on 0. And the question is just, how big could that interval be? Let me just ignore what's written here for a second. Here's 0, that's what I'm centered on. Let's put some other marks on here. 1, 2, 3, 4, 5, 6. We're told about -4, and we're told about 6. What I'm told is that -4 is basically a good point. When I plug -4 into this series, I get convergence. But -6 is a bad point. When I plug -6 in, I get divergence. The nice thing about intervals of convergence, once you know where they're centered at least, is they're sort of symmetric, right? If 4 is included, or sorry, if -4 is included, so must +4. Why? Because, well, if I'm imagining my interval of convergence, it has to be at least this big. It has to be at least big enough to get to -4. But like I said, it's symmetric, so then it has to go over to +4 as well. So, at a minimum, the interval of convergence would look something like this, I guess. I guess I don't know that. I guess +4 is sort of just on the boundary. It might be problematic, but it's like close. So I should technically put an open interval there. However, it could be bigger than that. It could be something like this. It could be even wider. That could be my full interval of convergence. But, looky here, 6 I know diverges. 6 cannot be in the interval of convergence. In which case, some interval like this would be invalid. So this automatically bounds what the possible radii of convergence are. I know that r has to be between 4 and 6. And it could be equal to 4, right? Because -4 was included. So the radius could be 4. It can't be 6. It can't be equal to 6, because that would mean 6 is included. And it's not. We're told right up here it diverges when x is 6. So now let's look at the actual problems. So the actual problems, let's look at B first. I think B is more straightforward. B gives you the exact same series, but this is basically saying x equals 8. And I know right off the bat that's problematic. It's even further out than 6 is. So if 6 is not contained in the interval, 8 is not contained in the interval. And we're talking about the interval of convergence. So if you're not in the interval of convergence, you're divergent. Part C, -3 is actually good. -3 is right here. And we already said, possible interval of convergences must include -4. -3 is even closer to the center. So that has to be in there as well. -3. Right, this is x equals -3. That causes the series to converge. This series is like a little uglier than the others, but no problem. Both of these are to the power n, so that's the same as -9 to the power n. And that's looking at plugging the x value at -9 into the given power series. Again, just like +8 was bad, +9 would be bad, and symmetrically -9 would be bad. So this must be divergent. The only one that's left is part A. I weirdly think part A is the hardest one. What value of x am I plugging into this series to get just the sum of c sub n? Well, I guess x equals 1, right? If I plug in x equals 1, this term here that I highlighted in red would be 1 to the n, which is just 1, and you're just left with the cn's. So x equals 1, certainly in the interval of convergence, it's less than 4, so convergent. There you go. I hope that was helpful. I highly recommend trying some other problems in Stewart just to get some level of comfort with these. But good luck to you. I hope you enjoyed the video. Thanks.